issue, how to compute this term UK U squared K, nonlinear term. Okay. Now, we discussed that in the past. So this term, U squared Fourier transform of U squared, it is a convolution. UP, UK minus B. Okay. And for every K, I have to, how many multiplication will be there? It will be N multiplication. N is number of Fourier modes. Okay. And there are N Ks, so there will be N squared multiplication. And addition as well. Okay. Which is very expensive for large N. 1D, no problem, but in 3D, there will be a, if you have, let's say, 1 million points, 1 million is, so there will be, N is, it depends. If my grid size is 10 power 6 cube, then that 10 power 18 and 10 power 18 squared is 10 power 36. So it just blows up. Okay. Or even if it's 1000 cube, which is usual nowadays, we make a grid, a 3D grid of 1000 points in each direction. So the number of grid points in 3D is 10 power 9, right? 1000, 1000, 1000 in each direction. And if you square it, it's going to be 10 power 18, which is very big, even for supercomputers. I mean, the topmost machines struggle to compute 10 power 18 multiplication. Okay, but there's a nice trick to solve this problem. So we can take Fourier. So that's it. That's how. Well, I mean, we don't compute this nonlinear term using convolution, but it's done using Fourier transform, okay, which saves time. And how do I do it? So I have this Fourier mode U hat K. I do the inverse Fourier transform. So I get U in real space, Ux. Okay, so I go from there. So I go to inverse Fourier transform Ux, and then since I have Ux, now I can compute Ux squared. This is in a, remember, it is in a discrete set of points. We have Ux available at discrete set of points. So now I can just square Ux at each of these points. So that gives us Ux squared at each point. Okay. Now I can do fast forward transform. Okay. So that gives us U squared K. Okay. So from here to there, I get U squared in Fourier space. Okay. Now, if you look at Burger's equation, I need to get ik by 2 uk squared, U squared K. So I just multiply ik to this quantity. Okay, this is a factor 2 which is ik by 2. Now, how many operations does it take? So multiplication at n points will take n multiplication. Okay, so this is order n. This one, given Fourier modes, I get Ux in order n log n. Here, this is also order n log n. And this order n. So the dominant order is n log n. So that's max expensive part of this. But n log n is much smaller compared to order n squared. Much smaller compared to order n squared. So imagine that n is 10 power 9, then log n is just log n to the base 2, so this is base 2. So 9 times 3 or 4. Okay. So it's 27. So log n versus n, the factor is 27 versus 10 power 9. Okay. So we solve nonlinear Fourier transform of the nonlinear term using the scheme of fast Fourier transform. Okay. So the convolution is not computed. We use Fourier transform to compute the nonlinear term nk. Okay. So you need to do it. Okay. So this is required. So the algorithm is pretty simple. In fact, the Python code is pretty simple. So this part is basically similar to what we did for diffusion. The set of grid points, there are 64 grid points. My box is 2 pi, and so on. Okay, now we just set this exponential factors. So I want to do vectorized multiplication. So I just create these arrays. Memory is not a big problem in modern computers. We have significant amount of memory. So if of course it's 1D is for no problem, you can do it in your laptop. So I just save this exponential factors. Now let's look at the initial condition. I need to from real space I need to go to Fourier space. So my initial condition is sin x. Okay, the initial condition is sin x 0 to pi. I take a Fourier transform, so I get initial condition in Fourier space, RFT. Now I need to compute the nonlinear term as well, so I create a function. So this is the function def nk. Okay. Now this is the problem. This should be shifted. This should be indentation issue. So f is so from Fourier space I can get a real space f, and once I get real space f, multiply self-multiply. So I get f squared. So this is f squared. And after f squared, I can take the Fourier transform from real to Fourier. So R50 of f, which is f squared now. Okay. Now that gives me fk product. Okay. So it is nothing but f squared Fourier transform. And after that, I multiply by ijk x. Okay. And that gives me ik. Okay, and I should do half somewhere. Okay, so half is coming here. Okay, that this half is coming here. We should. So this is only the. It's basically what I compute is d by dx of u square. We fully transform this. So how do I do the time stepping? So for every time step, I compute nonlinear term in Fourier space by this function, using this function. So compute nk. Given fk, I can compute nk. Okay, so given fk, so give me fk. I go to real space, multiply, forward transform, and so on. Now I'm using RK2 right now. So I compute fk mid. Okay, so I don't go to delta t, but I go to midpoint. Fk mid is fk minus dt by 2 nk, and exponential. So by the way, this is using exponential term. So it comes. Then nk mid is compute nonlinear term at the midpoint. And after you compute the midpoint, then I just do fk at t plus delta t is fk at t minus dt nk mid. Okay. So this is RK2. So using Euler, I go to the half step, then use the value of the nonlinear term at that point to compute u at or f at later time. Okay, so this is what gives me the function. So my initial, so let's look at the profile. It is output of that Python function. My t equal to 0, I have this field. Okay, so this field sin x, and at t equal to 0.2, I get the green curve. It is so positive speed guys will move to the right, and negative speed guys are moving to the left. Okay, so the traffic is going like that. 0.4, it's called a steepening. So the curve was like that, but it is steepening like this. So it's steepening further and further, and at time t equal to 1, we get this profile, which is almost there. I mean, the shock is, this is shock. The exact shock is this, which you get only when u is tending to 0, for very, very tiny. Of course, if you time stamp up to t equal to 2, then you get even a better shot. So that's what we get. So delta t min uh, by the diffusion term is 2h squared by nu pi squared, and that is 2 10 power minus 2. And coming from URMS, I get 0.015, but I choose much smaller than both of them, and it is chosen for this problem is 10 power minus 3, 0.001. So this is my delta.